everyone see that?
Yes, we can.
Perfect.
All right, Josh Speagle, take it away.
Sure. Thanks a lot for giving me the opportunity to talk today. As someone who does a lot more astrophysics than sort of exoplanet focused work, it was really cool to get invited to talk a little bit about some of the code I've been working on called JWST, and talk a little bit about how it might be able to help some of you, hopefully, with sort of your sampling parameter estimation problems. So I'm Josh Speagle. I'm a recent graduate along with Hannah, which is very exciting. And so we're both now, I guess, postdocs at the Center for Astrophysics, and I'll be moving to the University of Toronto, hopefully, once immigration stuff goes through this fall. So just to start, I want to just orient everyone to the same page, which is sort of showing the standard Bayes theorem formulation of the problem, which is that in most cases throughout, especially in astrophysics and all science, we're really interested in doing is inferring a set of parameters, which I call theta here, conditioned on some data that we've observed, D, and some model that we have, M. And we want to figure out sort of what are the constraints on parameters of interest, say, you know, the fraction of water in the atmosphere, or other orbital parameters for exoplanets. And to do that, we can use sort of two different ingredients. The first is the likelihood. Essentially, what's the probability that we observe the data, D, given the parameters of our model? And then also, what's our prior beliefs? In other words, how likely do we think, without seeing the data, that we would actually have these parameters of our model in the first place? And this bottom term, which is known as the evidence, or the marginal likelihood, is just, you know, sort of this integrated probability of seeing the data given the model. It's useful for some model selection. I won't talk about it as much here. For those who are interested, please feel free to ask me questions after at the end. So we want to estimate the posterior, and to do that, we need to go through this likelihood and this prior. And to do that, we often use these methods that generate samples from the posterior that we can then marginalize over and use to get things like parameter uncertainties. So I just want to start with a really simple example where you imagine that we have a prior, which is just a uniform box. And all we're interested in doing is sampling this likelihood, which here I've just sort of shown as this tiered structure, with darker areas being areas of higher likelihood. What methods like Markup chain Monte Carlo do is they try and sample directly from the likelihood. And this is a hard problem, you know, sort of capital H, capital P, TM. And that means that what you're trying to do is you don't know what this likelihood looks like, you don't know what shape it has, you don't know what structure it has. And so somehow you need some algorithm that can handle all of this complexity and essentially generate a chain of samples where you essentially wander around, and and the idea is you want to spend time proportional to how likely a solution is. So if a place is more likely, you want to spend proportionally more time there, and if it's less likely, you want to spend less time there. And so at the end, when you sort of gather up all the positions of the samples, you have more samples in regions where the likelihood is high and fewer samples where it's low. This is difficult. And so what nested sampling tries to do is, instead of solving a hard problem once, you want to solve an easier problem many times. And the easier problem is essentially, can you generate a sample uniformly within, essentially with a higher likelihood than some threshold, in this case, your previous sample. And so what this looks like geometrically is that your previous sample essentially defines some, what's known as an iso-likelihood contour. And you just want to generate any sample which is within this space. And so once you do that, you can just rinse and repeat. So you sort of want to generate a sample uniformly in this boundary. You then can shrink, and now you want to generate a sample uniformly in this smaller boundary based on the position of the original sample. And then you kind of can repeat that again. You generate a sample inside the smaller boundary, you shrink, and now you have this even smaller one. You want to generate a sample inside that. And so what you're doing is you're trying to solve this easier problem in theory, which is just generating a sample uniformly within some boundary which you don't know. You just want to do it many, many times sort of in order. And sort of the bet that nested sampling makes is that by solving this easier problem a lot, that you can actually be more efficient and get other things out of sampling than just solving a hard problem once. And that's sort of the fundamental idea, and where it gets its name is sampling in these nested slices that sort of start from the prior, start from the edge of this box, and then sampling sort of progressively smaller and smaller areas. So before I continue, I just want to point out that this might seem like a really contrived example because, we're assuming that the prior is uniform and it's kind of this small box. But really, as long as you have any function, what's known as a prior transform, that converts from your complicated real-life prior and parameters into something that looks like a uniform box, then all problems that you have essentially are the same as this problem, and you can sample just as you would imagine previously. This is one additional constraint that nested sampling has, is just you need to come up with some prior transform function that converts from your complicated prior to something that looks like a uniform. And it turns out there are lots of functions that actually do this. So this isn't so restrictive, but it is something to keep in mind. So this allows you to generalize from this very simple case to include lots of real-life astrophysical problems that you're interested in solving. So in practice, this allows you to do some cool stuff because just sampling inside these contours means that you're not really restricted to sampling in sort of one space at any particular time. You can actually sample places which have multiple solutions, which is shown in this particular example. But how do you actually do it in practice? Well, naively, you might think, well, one way to generate samples uniformly inside some unknown shape is just to, sorry, I see someone had done something in the chat, but I can't actually see.
And Josh, that was me posting a question for later. So I'm going to suggest go ahead and ignore the chat, and we'll come back to them at the end of your talk.
Okay, sorry about that. So one approach is, you might imagine, just one way to generate uniform samples inside some unknown space is just generating uniform samples everywhere. And some of them will land inside the thing you care about, and some of them won't. And this might work in the beginning. So if you imagine trying to get, sort of this number 2 here, all you need to do is just land inside this, some part of this gray contour. And so maybe you miss sometimes, but sometimes you'll hit. But, as you get smaller and smaller, as sort of the nested sampling progresses, this becomes harder because now you're sampling these really much smaller areas. So this strategy doesn't really work. You become exponentially more efficient at generating samples as time goes on. So you need some other approach. And this is sort of where the crux of all implementations really take off, and where kind of lots of the flexibility and coolness of nested sampling starts to show itself. So what happens in practice is you need some way of sampling from this constrained prior. In other words, you want to sample just from some region which you think contains, or at least is a good approximation of this iso likelihood contour, this sort of gray region here. You can see as you shrink, this red ellipse is an attempt to try and do that, to come up with some bounding distribution that kind of contains this smaller gray thing. And as you go, if you have, say, clever clustering algorithms, you can then break off this into be, 2 separate points. And that allows you to be able to track multiple solutions as they emerge, which is a really nice feature of nested sampling compared to typical MCMC methods, is the ability to kind of break off and fragment and look at multiple solutions as time goes on. This is kind of where all the challenges are, though, because there's no guarantee that you sort of get this right all the time. And how exactly do you determine, what's going on at any particular point, and where all these different fragments are, and how do you do the clustering? And that's kind of where all the implementation details and all the complexity comes in. So there are lots of different ways to do this. The most common, essentially, try and do this on the fly, where essentially you run thousands of chains. In nested sampling, they're known as live points. But you can think of them essentially hundreds of thousands of chains. And what you do is you use the distribution of these chains, here shown in purple, to actually estimate the shape of this iso likelihood contour in real time. And so what I'm showing here, there are some references on the bottom for people interested in following up on this, is these purple points are the distribution of these chains at a given instance, and the gray is essentially samples that you can draw as proposals for where to go next based on different sampling strategies. So for instance, this left one is essentially no sampling strategy, so just sample everywhere inside the box. And then you can see, as you move on to different approaches using, say, different ellipsoids, you can try and cluster them. For example, here you can break things off into multiple ellipsoids. You can use overlapping balls or cubes. Then you can kind of come up with very flexible functional forms to generate these type of bounding distributions. But these are all sort of, empirical approaches that you try and use to estimate these. Once you have an estimate of this, you then need to generate some samples from it. And there are many different sampling strategies that also work here. You know, one example that's really that's most popular is using essentially multi-nest or these uniform samples. So if you have some type of bound, you just generate samples within that bound. But there's no reason you have to do that. You can also use, say, the shape just to kind of make proposals, and you can use, say, MCMC to kind of walk around on the inside to generate a new position. You can use what's known as slice sampling to generate new samples along certain directions, say either randomly or along certain principal axes. Or you can use some variant of Hamiltonian Monte Carlo, give this point some velocity and kind of have it ping pong around on the inside. This tends to be a lot more inefficient than people who may be familiar with Hamiltonian Monte Carlo, but these are all different approaches that you can use to generate these types of samples. So you get a lot of flexibility in terms of what you can do. And so prior to sort of Dynasty, a lot of these were sort of separate and collected in different areas. And really only Johannes Buchner was really trying to like collect these into one uniform package. And so Dynasty was an attempt by me to kind of take all these different methods that have been developed by many other people in the literature, including myself, and put them in sort of a public open source Python package that was designed to be really easy to use and really heavily inspired by EMC, by Dan Mackey and collaborators. So the idea was you should be able to use Dynasty just as easily as you might be able to use MC, but you can also customize it by mixing and matching all these different methods. It's designed to be really modular, so you can say change your sampling approach, your bounding approach, the number of live points, lots of different constraints on how you want to sample. And I also have a bunch of built-in plotting utilities and post-processing tools for people who want to be able to take those outputs directly and generate sort of publication level plots that they can just put into their papers. So as it's just a demonstration, Dynasty is designed to be pretty easy to use. And in fact, you can use it in 3 lines. So all you need to do after you import it, which you can grab either from GitHub or through pip, is just initialize this nested sampler object, which takes your log likelihood, this prior transform function, which is essentially just your prior, just in a different way, and the number of dimensions. You then just use the run nested function. In this case, I'm using all the defaults. And then when you're done, you grab the results. And that's it. And if you want to use sort of this dynamic nested sampling, which I'll explain in a bit, that's exactly the same, except that you just call dynamic nested sampler instead, and the exact API is almost identical. So I tried to design to be very easy to use, but all of these initializations have tons of options that you can read about more in the documentation. If you want to examine the results, that's again just sort of straightforward. And I'll actually use the plots generated from Dynasty to explain sort of how nested sampling works and what exactly the dynamic part means and how that plays into the pros and cons relative to MCMC. But all you just need to do is import this plotting module, and you can generate a couple things. For example, this run plot or trace plots for people who might be familiar with those. Or corner plots if you're interested in visualizing sort of these marginalized representations of your posterior. So just as an example, I'll consider this case where we have a correlated 3D Gaussian. So this is kind of what the corner plot looks like. So all we're just going to do is we're sampling inside this uniform cube, and we're just trying to sample this correlated structure here. If you use run plot, you'll get a plot that kind of looks like this. And I'll sort of go through what each of these mean. So the x-axis here, this is essentially the log prior volume, or the negative of that. And so from the left, essentially, is 0 is starting from the prior, and going to the right is as things get progressively smaller and smaller, as your sort of nested shells are shrinking. So I'm going to swap to a version of this that's labeled, taken from the paper that's published in MinRAS. So you can sort of see on the top, what you're essentially showing is the number of active chains, essentially. So you can see sort of as you move from left to right, how you're shrinking over time, and you have smaller and smaller prior areas. And this little line here indicates when sampling terminates, and you kind of just add up the chains one by one at the end of your at the end of the run. The second panel here shows the relative likelihood. Because nested sampling samples increasingly, like strictly increasing likelihoods, you sort of can see where most of your likelihood is located as you sort of go, as you shrink. This third panel shows the importance weight. This is essentially what you really care about, which is the product of your likelihood times you can think of like the relative differential prior volume. So in other words, here at the left, this is where you're just prior dominated. All you have is just prior, you have little likelihood, so there's not much chance of having a solution there. In the central region, this is sort of where most of the posterior mass is, where you're taking your likelihood density and multiplying it by a posterior volume. And so here is sort of where your fits are good, and also where you have a lot of them, where you still have a decent amount of prior space. That means that for every good fit, there is actually quite a few of them. As you get to the end, this is where you have the best fits, but there are very few of them. And so this is where you have the highest likelihood, but also very, very low density in terms of the number of possible solutions. The bottom is essentially the evidence. This is the integral of this top thing. So you can see overall with some error bars how close this is to the truth if you're interested in estimating those. So this kind of shows, gives you a snapshot of how exactly the run looks over time. You can also look at the trace plot. This is essentially just showing how your chains evolve over time as they sort of shrink, along with these 1D distributions on the right. The coloring here is actually the same thing as I showed before. It's this importance weight or the posterior mass. And each of these red lines that I've highlighted here shows an individual chain as you sample. So again, these are all sort of things that you can just pull right out of the code. And finally, this is just grabbing the corner plot where you can kind of see just a representation of how well we do at the end of a run for this particular case. So given this intuition, what exactly does the dynamic part of nested sampling come in, and why is that relevant to the code? Well, if you look at sort of how nested sampling works in practice, and I apologize, this plot is flipped, so now you're sampling from right to left. What's actually happening is you're kind of sampling at equal intervals on this plot is kind of how nested sampling works as you're doing this integral. And so what that means is if you add in more chains or more live points, what you're really doing is you're adding in more points everywhere. And that means you have an equal amount of points that are in this prior dominated space, which you might consider wasteful, unless you care about the evidence or you care about this integral. And you're adding the same amount of points here as you are in the central space where you actually care about where all the posterior is. So you're adding just as much points in the tails as you are sort of in the center. And you may not want to do that. You might just care about adding points directly where you think they're most important. And that's kind of what dynamic nested sampling tries to do, is it says, why can't we just add in all the points right where we know that they matter the most? In practice, this gets a little complicated in terms of how do you know where to add points, but you can kind of do this in an iterative process where you can add points on one at a time, and each time you add a new set of points on, you can kind of refine your estimate of where you should add more points, and you can rinse and repeat. And so this is now the same plot as before, where all I've just done is I've just changed the overall strategy and how we allocate points. And so we're sampling exactly the same 3D Gaussian, and this is exactly the same plot as before. This black line here is what happens if you just keep the number of points the same everywhere. And these, again, are shown using the exact fixed number of samples. So you can think of essentially the area under the curve is conserved. So if you care about the posterior, you can look at this blue curve, and we can just add in a lot of points right where it matters, which is around this central point here. If you care about the posterior and a little bit of the integral, which is the default behavior in Dynasty, you get this red curve. So you now are adding in more samples where the posterior is denser. And if you just care about the evidence, then if you're doing an integral, what you care about is the tails. You really want to make sure you get the normalization right, that you actually have a really good approximation of exactly where this integral is starting from relative to the prior. So you actually add in all the points way out here, and you actually add in fewer and fewer points as you get a better estimate of the posterior, because there's just less of the integral left. So you just need fewer points to estimate it. And so this is an example of how just by changing the strategy of where you put points, you can actually make nested sampling look a lot more like MCMC. And you can see this visually by comparing, say, the case where you have the default behavior, which is by adding the same number of points everywhere, where you add in points directly where you think the posterior is, and where you add in points where you think the evidence is. You can see just visually that we're adding in a lot more points here at the outskirts and a lot fewer at on the inside. And here we're just dumping all the points directly where we think the majority of the posterior is. And this all happens on the fly. These are all estimates that come in from running the code. So that's kind of the basics. So what's the upshot to all of this? Well, in some cases, say in a simple linear regression model, what this means is if you're using Dynasty, and you're looking at the sampling efficiency, essentially how many likelihood calls are you making versus getting an accepted point, and sort of what's a sample size, the effective sample size of that when you account for some of these like correlations and different sampling methods. And what you find is that Dynasty in lots of cases can get, roughly order of magnitude more efficient than methods like MC or standard, Metropolis Hastings MCMC. This, of course, depends a lot on the problem, but the fact that you can get sort of this substantial increase in sampling efficiency has led us to use it in many cases where we did find that using Dynasty was quite nice. So these are just some examples that you can actually apply Dynasty to several real-life problems and end up with good results. This is a case where we're doing galaxy SED modeling, which was a project led by Joel Lesia, using a code called Prospector. And again, this is a large parameter space, but you'll notice on the bottom that in this particular galaxy, there's actually this bimodal distribution for the metallicity of the gas, this gas log Z parameter, that we're actually able to capture quite well. Another good example where this has been used is in 3D dust mapping, which was part of a thesis I did in a paper that Catherine Zucker, another graduate student here at the CFA, and I co-led last year. And essentially, if you look at this top right plot, this is showing the distance modulus, so log distance, and this is showing the extinction. And all we're looking for is really a step function where you see more stars, which are indicated by these probabilistic estimates, where that kind of increases as a function of distance. And in this particular case, you'll notice we have two solutions, and Dynasty is able to characterize it quite well because we don't know, for example, whether this particular 3D dust structure starts here, where we have these two stars, or here, where we have a different set. These are just some real-life examples where Dynasty has been applied, where you can see some of the advantages coming out. So to end, I just want to say I don't want you to come away from this talk feeling like nested sampling is the best thing since sliced bread. It's not. And in particular, there are some advantages and disadvantages to it. The advantages are you can characterize some of these complex uncertainties in real time. And in some cases, you can get a lot higher sampling efficiency. There are also cases where you get a lot lower sampling efficiency. So it depends on your problem. And it also possesses well-motivated stopping criteria if you're interested in estimating certain things like uncertainties or errors on the evidence. But also possesses notable disadvantages. In particular, this prior transform limits the way that the prior works. And the runtime, because you're starting from the prior, depends on the size of the prior. So this means you have to think really hard about how big of a prior you want. Because if you make your prior, say, 100 or 1,000 times bigger than the actual likelihood, for MCMC, that might not matter too much because you'll quickly converge to the true solution and kind of start sampling. But for nested sampling, because you're starting from the edge and kind of shrinking, that's going to make you run a lot slower. The approach also can lead you to miss certain types of solutions. You can definitely ask me more about what exactly those look like, but there are certain edge cases where nested sampling will perform worse. And of course, this is a lot more complicated. So if you want to debug certain things or are curious about specifics about how things work, it's a little harder to intuitively understand than MCMC, and that can be important when you're trying to solve a particular problem or explaining it. So that's the end. If you're interested in using the code, definitely feel free to give it a spin and contact me and take a look at the docs. And again, I wanted to say that this was really inspired by MC, and I intended the package to be really a supplement, the type of utilities that provides, and not a replacement. And so with that, I'm happy to take any and all questions.
All right, thank you, Josh. Hey, folks, go ahead and unmute if you want. Let's give a little round of applause here. Thank you, Josh. And let's go ahead. And I'm gonna take kind of 30 seconds or so before we start taking any questions here. So think for a minute, write something in the chat, raise your hand if you have a question about this. All right. Let's start with Hannah's question here. But what are those pathological cases where Dynasty cannot sample from the parameter space?
So essentially, yeah. So essentially, because you're kind of sampling in a way where sort of these modes emerge organically over time. what that can mean is that, for example, if you have two modes or two solutions where they have wildly different amplitudes, but you might care about like just knowing that one of them exists, or even though it might be very small, say like 1% or a fraction of a percent, just so you have an idea of like what alternate solutions exist. In terms of like raw volume, one solution just is like, 99.99% of the parameter space. And so because nested sampling just cares about that, it won't even spend a lot of time trying to characterize this secondary solution. So whereas with MCMC, because you're kind of, especially when you start, you're sampling up this gradient where you're just like, oh, I want to, just kind of improve my likelihood and just go down to wherever it is. You're actually more likely to discover these types of solutions, even though they're quite small. So those are some cases where you can miss. There are also other cases where, because of the way that the structure emerges as sort of you transition from the prior to the likelihood, sometimes that can be a little tough, or at least a lot tougher than, say, if you just knew what the likelihood was from the beginning. So there are some specific edge cases where that can cause the nested sampling to behave kind of weird. But they are, in general, I found quite uncommon, but they definitely do exist.
Bjorn, you have a question. Go ahead, or have your hand raised.
Yeah, let me start with a comment. I really liked your presentation, and we have been using nested sampling for 10 years now, almost, for atmospheric retrieval, since we first kind of used it for atmospheric retrieval. And this is by far the best presentation I've ever seen on nested sampling. So I'm not saying this easily, but anyway, so the question that I have is, especially about this dynamical modeling. So one thing that we're facing in general when we do atmospheric retrieval or when we use nested sampling for other fits is exactly this point that you addressed with the size of the prior parameter space.
Right.
And I found that it's really good for atmospheric retrieval often because a big part of the parameter space, because the systems are it's very poorly constrained often, the problems that we're interested in. So nested sampling is really good for this. But then there are other cases where, for example, you have many parameters, or you have a tiny fraction of the parameter space that has the significant log likelihood. Does this dynamical modeling help in that regard? Or so kind of to make it more specific, like how many parameters can you have, and what are really the advantages of the dynamic modeling for having a small region of the parameter space that has significant likelihood?
Right. So the big advantage, so the functional problem with the dynamical implementation is that before you can figure out where you want to allocate, sort of additional samples and adapt to the posterior, you kind of need to know where the posterior is first, like just have a rough guess. And so what that means in practice is that you need to at least have one nested sampling run, even if it's a really sparse one with a small number of live points, to just give you a sense of like, where should you just allocate points to start? And that often means that in like a large parameter space where you have a small sort of likelihood peak, you still have some part of the problem where you have to solve that really difficult kind of annoying case to at least locate that. Once you have it though, you can then sample quite efficiently because you'll find that you just dump all your samples into a very small region and you don't really have to worry about dealing with this humongous integration again, especially if you don't worry about the sort of normalizing factor. So in some cases, it turns out that initial first step is just so prohibitively expensive that even dynamic, modeling doesn't really save you. But in cases where it's not, it does cut down the runtime significantly. So we found that in lots of cases where this exact situation happens, we have, something like 40% of the runtime is just doing this initial run, and then 60% of the remaining runtime is just essentially adding samples to sort of this small likelihood region. And those, of course, will vary based on how big things are. But it can help in some of those cases.
And is then, for the number of parameters, is there then any limitation? Because some nested sampling usually scales very poorly with number of parameters.
Yes, so this doesn't fix that, unfortunately. So, I mean, some of the sampling strategies I have allow for better scaling with number of parameters. But again, it depends on what you mean by efficient. So, if what you mean is that if you have 30 parameters that you can sample with sort of say like 0.5% efficiency, but then that means you're doing 200 likelihood calls for every successful point. That's pretty good if you think about compared to like what you might expect from like exponentially declining efficiency, but it's still not great. So I have a bunch of methods that try and deal with this, but really, like, functionally, I found that once you get beyond sort of 20 or 30 parameters, you're really struggling to do a good job.
Okay, thank you.
Yeah.
Awesome. Cool. Josh, let's thank Josh one more time. And I'll ask that, Josh, as more questions come in on the chat, please feel free to answer those throughout the rest of the meeting. But time-wise, I want to get along so that we can hear Hannah's talk about ground-based observations of transient exoplanets. So, Josh, if you could, stop sharing your screen, and then Hannah, go ahead and share your screen, and then we'll move on to a new topic. Awesome. That looks great, Hannah. Cool. We will wait a minute for you, though.
Sorry, I realize I can't unmute myself once I'm here. Okay. Can everyone hear me?
Yes, we can hear you, and we can see your slides being presented.
Fantastic. Okay. Well, yeah, thanks so much for letting me present some of this work. So my name is Hannah Diamond-Lowe. Like Josh, I just graduated from the CFA, and I'm actually moving to the Technical University of Denmark. So like Josh, I am also negotiating international relocating during COVID. So that's been really fun. So this talk is going to be, about the reconnaissance of terrestrial exoplanet atmospheres from the ground, and in advance, of course, of JWST. So I'm going to I'm going to partially be discussing what we know about terrestrial exoplanet atmospheres now, how that helps us with what we're going to try to learn from JWST. And I'm also going to delve a little bit into the sort of data analysis and techniques that I and my collaborators have developed and used to give some insight into terrestrial exoplanet atmospheres, specifically from the ground. So I want to make sure we're all on the same page with what a terrestrial exoplanet is. So this is a mass radius diagram in Earth radii and masses generated from some code I pulled from Zach's GitHub, which is really cool. And basically what we're showing here is sort of some broad brush exoplanet categories, along with a couple of theoretical composition curves. So a sort of hydrogen and helium dominated composition curve, that's this kind of yellow one, and then a rocky composition curve, so some combination of an iron core with some kind of silicate mantle. And the key thing is that these planets on the terrestrial composition curve, whoops, sorry, oh no. There we go. These are, so here we also have the solar system planets in blue. And these planets might have an atmosphere, or they might not. If they did, that atmosphere would contribute a negligible amount of mass to the planet. And it would be a very sort of thin annulus around the planet. Whereas when you have these sort of sub-Neptune planets, which is not a great name for them in my opinion, but basically they are underdense compared to this rocky composition curve. They might have a lot more hydrogen and helium sort of on top of some kind of iron silicate composition core. And what I'm sort of asking is, what can we observe about the planets in this group? So for now, the main question that I want to ask is, do these planets have some kind of low mean molecular weight or hydrogen and helium dominated atmospheres? And I want to clarify that, I'm not asking, do these terrestrial planets look like the sub-Neptunes? Like, if they had very massive hydrogen and helium atmospheres, they wouldn't fall along the terrestrial composition curve. And these sub-Neptunes might really have, many hundreds to thousands of bars of hydrogen and helium at the surface, whereas we're really kind of asking about fractions of a bar up to maybe a few bars. Okay, so that's that. Okay, so the method that I've mainly used to do this is transmission spectroscopy, which I think a lot of people here are probably familiar with, but in this very not to scale schematic, we're basically looking at these two governing equations, which is the transit depth, so the planet radius to the stellar radius squared, and also this atmospheric scale height, which is, Boltzmann constant times the planet's equilibrium temperature over this is the mean molecular weight. This is the kind of true free parameter we want to figure out based on the composition of the atmosphere, and also the planet's surface gravity, right? And that's kind of where, the gravity is, of course, dependent on the mass and radius. So that's a sort of key parameter in defining the planet as terrestrial and having a terrestrial planet, potentially atmosphere. So the instruments that I've used to do this in my research are the IMAX and LDSS-3C multi-object spectrographs, which are mounted on these twin Magellan telescopes at the Las Campanas Observatory in Chile. And what's kind of fun is that each of these twin Magellan telescopes are 6.5 meters in diameter. So in some way, JWST would be like launching one of these into space, except, nothing like that. But it should be sort of similar collecting areas. So some of the aspects of doing transmission spectroscopy from space will be similar to what I've done here from the ground, and other aspects will be very different. So this is sort of the tool. I've already explained we're going to be using transmission spectroscopy. So we need a sort of specific data set to work on. So in this figure, we have the transmission spectroscopy metric, which is sort of a proxy for signal to noise here on the y-axis. And I've plotted this as a function of planetary equilibrium temperature. I want to note that all of these planet discoveries, which I've kind of listed over here, these have all happened within the last 5 years. So even within the field of exoplanets, these targets are pretty fresh. And finally, I want to note that there's a sort of specific cutoff for these planets to even get on this figure, and that cutoff is sort of to determine which of those might be spectroscopically accessible for atmospheric investigation. And that kind of rough cutoff for now is to have these systems be within 15 parsecs. And for your host star radius to be less than about 0.3 solar radii, right? So that gets back to your transit depth, which is depends on the stellar radius. If you're gonna hope to see these very shallow signals from these small planets, you really need to be looking at smaller stars that are nearby so you can collect enough photons. This pretty much guarantees that, at least, for a main sequence star, you're gonna be looking at a mid to late M dwarf. For interest, these ones with red diamonds are part of a multi-year transmission spectroscopy program that I've led on the Magellans, and that should conclude at the end of this year. Okay, so now we're going to take like a detour into what actually goes into taking these data, the data reduction process and the analysis process that moves from, the raw data that you get like while you're sitting there at the telescope to an actual transit depth that can go into building a transmission spectrum. I'm going to highlight sort of the steps I think are maybe a little bit most relevant if you're sort of only thinking about JWST. So there's a lot of steps, and we'll kind of start up here with step number 1. And this would be to identify the stars that you're going to look at. And right off the bat, I can highlight the major difference between what I'm doing here from the ground and to what will happen with JWST is that here we are using multi-object slits. So these are these special slits cut out of a custom-made mask that we put into our instruments. And we need to do that because we need to look at not only our target star of interest, in this case, all of this is taken from LHS 1140, which has a planet around it. So we want to look at this star, but we also want to look at a comparison star, and that is because when you observe from the ground, telluric features in Earth's atmosphere imprint themselves on your spectrum as it comes from the star, through the atmosphere into your telescope. And variations in those telluric features over the course of the night will almost certainly wipe out any signal that you are trying to see. It could completely wipe out the transit if you have, say, large variations in precipitable water vapor. But even without that, you're just going to get, as you change in air mass, or if there's any kind of wind or just anything happening, you're not going to be able to remove that information from what you're seeing, from what you're actually interested in from the star, which is, a decrease in photons that indicates a planet. So you won't need to do this from space because there is no Earth's atmosphere and no variation on that scale to remove. And also, for instance, like the nearest SOS instrument, which is sort of designed to do this kind of work, is a slitless spectrograph. So so that's going to be very different. But then some things will be similar. So there still will be some kind of dispersing element that will be put into the light path and give you a spectrum. Also here for the ground, we have to go through a lot of work to remove this background flux, which for us is mainly from the sky. There might still be some need to do this. There might still be some kind of like background flux, contaminating flux from space, but it will for sure not be on the level that we see here in the sky background, which is this spectrum here. And it looks very small compared to, say, the stellar spectrum, but this is like actually far above the levels of information we're looking for when trying to detect a transit. Yes, we extract some spectrum. There's going to be some wavelength calibration to get wavelength calibrated spectra. There will be similarly, we will still need wavelength calibration with JWST. And then finally, we come over here to binning the spectra into smaller wavelength channels to construct the transmission spectrum. I predict that will be similar for JWST. Okay, so now we've sort of like scrolled up here. So here's step 6 from before, and here I'm kind of indicating, you're going to sort of sum over a smaller wavelength channel and generate a point. And if you do this, over all your observations throughout, the course of your visit or program, there will be then a light curve that you get. And you can see from the ground, a lot of these sort of features in the target star, LHS 1140, track with these similar features in the comparison star. And that's because all of these features are telluric in nature. This tail off here is because of the change in air mass during observation. And you can see this is a relatively clear night. You can kind of pick out, this transit here. So then we divide the LHS 1140 time series by the comparison time series, and we get this light curve. And then this is kind of where a lot of the work goes in, which is to actually model this light curve. And so I'm going to take a sort of even detour from the detour to talk a little bit about what happens here. And kind of the basic point, and this is going to sort of be the same for anyone who does sort of data modeling, is that we always want to model the light curve at the same time, any kind of systematics in the light curve at the same time that we model the transit. That's been best practice for a while now. And there's also a sort of key in choosing the method that makes sense for the data. And I'm going to sort of highlight 2 that I have worked with. And they, I would say, are in some ways the kind of extremes of what you can do. There's also principal component analysis, which has been used a lot. I think that's a kind of nice in-between option. But you can basically do a sort of linear decorrelation where you're saying, all of these systematics are just some kind of linear combination of, say, air mass and maybe a polynomial. Or you can do a full-on Gaussian process, which is not a decorrelation at all. It's an actual construction of a covariance matrix to see how closely points are related to each other, either perhaps in time or even in some physical parameter like air mass. And of course, there's pros and cons to each method. A linear decorrelation is fairly easy to implement, and it is quick to compute. It lends itself very nicely to vectorization. And the cons are that you're basically assuming uncorrelated noise, and you can sort of add scalings to your likelihood to account for this, but its sort of core principle is not actually the best assumption. With Gaussian processes, this is like an example of a kernel that I've used, but there's several to generate the covariance matrix. So I've given some sort of better source material there, plus the George package, which I have used to implement this. And the Gaussian process is great because it really allows for this understanding that your noise might not be completely uncorrelated, and so therefore you're going to get a more conservative and perhaps more therefore accurate estimate of your error bars. And as maybe you might have guessed, the con is that this can be incredibly slow to compute, and so you can do these tricks if you want to do this for large data sets. But whichever technique you choose, these are only going to generate models, and but you need to sort of sample around to see which exact version of the model is going to best fit your data. And so you can do this with MCMC, as Josh alluded to earlier, or you can do this with a dynamic nested sampler like JWST. Sorry, Josh, I thought your paper came out last year. I guess I got that year wrong. But I personally use JWST for this work. I found it to be, especially when using lots of free parameters, so sort of high dimensional space, I have found it to be a little bit more efficient. So MC will have a hard time converging. If you have many parameters, I found that, though it is not fast, as Josh mentioned, I could still, run some of these, a dynamic nested sampler for about 30 to 40 free parameters and still get convergence within a reasonable amount of computing time. So that was all this step here. And so once you do that, then you can finally actually get your transit depth as a function of wavelength and make a transmission spectrum. So if you are not interested in modeling systematics, we're going to go back to the sort of science of it. And this is an example of a transmission spectrum of the terrestrial exoplanet LHS 3844b that we just submitted. And what you're getting out here, so here's this transit depth parameter that I mentioned at the beginning. And we're looking at it as a function of wavelength in these 20 nanometer bins. The black points are these error bars, estimated using a Gaussian process, and then a JWST has been the tool to estimate the parameter space to get these error bars. And we're comparing them to a few models which have been generated by Helios and Exo-Transmit, the architects of which were both authors on this paper. And what we're basically able to do with this information is to say that we're going to compare this transmission spectrum to a few different kinds of solar composition atmospheres. The sigma indicates the level to which we are like ruling out these atmospheres, and also some pure H2O water steam atmospheres. And you can see right away that when you get, sort of up into 1 or 10 bars solar, your transmission features are blowing up in the models, and these are the models that we're able to rule out the level of variation. And for instance, the water steam atmospheres, these are just too small relative to our typical error bars to really say anything about. So if we sort of go back to the targets that we're interested in, I've highlighted here which planets, based on my work plus work with HST by Julian DeWitt, which planets we can definitively say do not have these low mean molecular weight hydrogen dominated atmospheres. LHS 1140b down here ended up being below our detection limits, and data is still forthcoming on this particular system. So kind of to conclude, I would say that, based on work that I've done, the planets GJ1132b and LHS 344b, these two guys here, these do not possess low mean molecular weight atmospheres. And if you couple this information with the results that we have from the TRAPPIST planets, it really is starting to look like that clear low mean molecular weight atmospheres just don't occur on these terrestrial exoplanets. You could say that as we went to perhaps cooler equilibrium temperatures or different conditions, that might not be the case. But sort of the empirical evidence right now is pointing in that direction. And then finally, choosing the appropriate modeling method and sampler to kind of estimate your transmission spectroscopy error bars is going to be key to building that transmission spectrum and then actually making a determination about the planet's atmosphere. Yeah, I will stop there. Thanks.
All right. Thank you, Hannah. Everyone, go ahead and please unmute and let's give Hannah a round of applause for a great talk.
Thanks.
And again, I want to give folks a little bit of time, think about questions you might have, write them in the chat, raise your hand if you have questions. We're at about 5 minutes to the hour right now. So if you have another Zoom meeting coming up from this, time to stand up and do your stretch or whatever. But I'll wait about 30 seconds or so and then start taking questions for Hannah. All right, let's start with Kevin's question of which of these targets would you want to follow up on first with JWST and why?
Oh yeah, I can also show you, well, okay, I guess I stopped sharing my screen. If you want to see the screen, let me know. Yeah, so that's a great question, and I sort of want to start by just like a plug I have, which is that, any of this sort of work might have easily been done with like just observing maybe 1, maybe 2 transits with JWST, but I don't think that's like a great use of that resource. So what I think we should be using JWST is to go after these planets which we won't be able to address spectroscopically from the ground. There's of course like different techniques. So for instance, if you want to like observe a phase curve or a secondary eclipse, that might be more doable with JWST, definitely more doable with JWST than from the ground. So those kind of techniques are going to be very fruitful with JWST. But if you're going to just sort of like, oh, I'm just curious if this planet has a low mean molecular weight atmosphere, I don't think that is a great project for this kind of telescope, unless you're really trying to like push out to maybe a terrestrial planet that's a little farther away or around a larger star. Okay, so that's sort of my my plug. Yeah, so with that, I think the real question that we still have for terrestrial exoplanets orbiting M-dwarfs is, can they retain atmospheres at all? We've so far ruled out low mean molecular weight atmospheres for a lot of planets, and in the case of LHS 3844b, we've even ruled out with Kreidberg et al. 2019, heavier atmospheres with like 10 bars or higher. So the challenge is going to be going to cooler planets. So LHS 3844b has an equilibrium temperature of like 800 Kelvin. But as you move out to cooler planets, it might not be such a given that their atmospheres may be lost. The flip side of that is there's been a lot of work sort of to calculate how much telescope time on JWST you might need to address the atmospheres. And for the coolest planets we have, so for instance, like the habitable zone planet LHS 1140b, that also is kind of not feasible with JWST. So while that's the direction I think we should be going in, I think there's also sort of a limit there to how far we can go. So if you want some specific planet names, I would be really interested in looking at, of course, the TRAPPIST planets, because there's a huge variety there. GJ 1132b is the planet I like because we don't think it has a low mean molecular weight atmosphere, but it has a relatively cooler equilibrium temperature around 580. And then, of course, if TESS delivers kind of anything else in that range, yeah, that'd be great. Thanks, Kevin.
Sounds good. Thanks, Hannah. Okay, so we're at the hour now. So
Cool.
Everybody, feel free to travel on to your next adventures. Hannah and Josh, do you have a few minutes to stick around a little bit longer? I think there are a few more questions that folks have, but I think this is now converting to the like gathering up your laptop and your teacup end of the seminar sort of a setting. So have a lovely afternoon or evening or morning or wherever you are, folks, and we'll see you again in 2 weeks. And I'll certainly stick around for a little while longer too, if anybody else wants to chat.